Good afternoon all of you. I warmly welcome you all for today's session of microbiology lecture. I am Sandhya Rani, lecturer in microbiology at TSWREIS, Adilabad. Today I am going to discuss about a technique which has wider applications and it is also one of the most popular and routinely used laboratory techniques. The technique which I am going to talk about is electrophoresis. In this session, we are going to learn about the principles and basics of electrophoresis, the importance of electrophoresis and the types of electrophoresis, in which I am going to emphasize on Agarose gel electrophoresis and its applications. The technique electrophoresis became popular by the works of a Swedish biochemist, Dr. Arne Theselius. He is also well known as father of electrophoresis. He is very interested in separating serum proteins from the horse blood. For this, he chose a technique called moving boundary electrophoresis. For his works, he got awarded with Nobel Prize in 1948. Electrophoresis. The word itself is indicating that there is an involvement of electric system, and phoresis means migration or movement. So, the migration of charged particles under the influence of electric field is called electrophoresis. What are charged particles? Any particles which carries charge on its surface are called charged particles. This charge may be positive or negative. For example, proton is a positively charged particle and electron is a negatively charged particle. What is an electric field? Electric field is the region between two oppositely charged electrodes. One is positively charged electrode and the other one is negatively charged electrode. We call it as cathode, anode and cathode. The region between these two electrodes are called electric field region, electric field. So, if we place any charged particle in between this electric field, this field exerts some force on the particle. For example, if we place proton here, proton is positively charged. So, the positively charged electrode exerts repulsive force on it and the negatively charged electrode exerts attractive force. Finally, this proton moves in this direction towards negatively charged electrode. So, under the influence of an electric field, charged particles migrate towards either anode or cathode, and the speed of migration can be explained by the formula V equals to EQ by F. Here, V is the velocity of the migration of a molecule and E is the energy of the electric field and Q is the net charge of the molecule and F is the frictional coefficient. This depends on the shape and size of the molecule. So, velocity is proportional to the electric field's energy and charge and inversely proportional to the frictional coefficient, which are mass and shape of the molecule. So, imagine two rocks, one is a small one and the other one is a bigger one. If you want to move these rocks from place A to place B, which one takes more time and energy? Bigger one, right? Why? Because of its mass, it demands higher energy and also takes more time to move. Just like that, the particles which we are going to separate are also, if they are having high mass, then it would drag the molecule behind from the migration. Okay. If we see the electrophoretic mobility, mu, which is equals to energy electric field and the velocity of the molecule. So, if we substitute this formula here, E cube by F into 1 by E, it would be Q by F, charge and frictional coefficient, which is mass and shape of the molecule. So, electrophoretic mobility is proportional to the charge and inversely proportional to the mass of the molecule. So, what are the molecules which we are talking here? And do the molecules carry charge on their surface? Let us see these questions. So, the molecules which we are going to separate are in various kinds. For example, drugs, steroids and biomolecules. We are interested in biomolecule separation. What are biomolecules? Molecules which are in the living system are called biomolecules. The major types are carbohydrates, lipids, nucleic acids and proteins. So, how we are going to separate them? In order to separate them, those molecules should carry charge on their surface. And why do we need the separation? What is the need of separation? For example, our system is loaded with biomolecules. They each have specific function. If there is any change in the composition or structure of those molecules which results into a change in the body's function, and also it might be a disease. So, in order to troubleshoot where the actual problem lies, we need to isolate those biomolecules from other molecules and then separate them in order to see the problem. So, does these biomolecules carry charge on their surface? Let us see. For example, DNA. DNA is a double helical molecule. The basic fundamental unit is nucleotide. So, if you see the double helical chemical structure of the DNA, all the bonds which are ionizable groups are involved with the bonding with other molecules except the O minus group on phosphate group. So, this O minus free ion gives negative charge to the whole DNA molecule. So, DNA under physiological pH, it is always negative. So, DNA carries negative charge. So, inside the electric field, in which direction this DNA moves? Towards anode, which is having positive charge. And let us see the other example, proteins. Proteins are made up of amino acids. If we see the basic structure of amino acids, here it has one amino group and one carboxyl group. These are ionizable groups. So, and this R group can also have a charged side chain. So, based on the charge of the side chain, we could again divide the amino acids into negatively charged, positively charged and neutral amino acids. For example, aspartate is a negatively charged amino acid. And the charge on these ionizable groups is highly influential by the pH of the surrounding medium. So, whenever we are going to separate the proteins, we always have to take care that the pH of the surrounding medium should be kept constant. Okay? Let us see with an example. Here I am going to take the basic structure of the amino acid. Now, the net charge is 0, 1 plus and 1 minus cancels each other and the net charge is 0 now. This state could be called as Zitter ionic state and the pH is the isoelectric point. Okay? And if I increase the pH, then the OH minus ion concentration would be high. These OH minus ions attracts the protons from these groups, and here this NH3 plus loses its proton and becomes NH2. So, what is the net charge here now? only it has negative charge. And I decrease the pH. If we decrease the pH, at acidic pH, the protons concentration would be high, and these protons goes and binds with the negative charges. Here it goes and binds with the COO minus group. So what is the charge here? Positive, right? Depends on the charge these carries, they move towards either anode or cathode. Next, we will see factors affecting electrophoresis. Both intrinsic and extrinsic factors affect the process of electrophoresis. Sample properties comes under intrinsic factors. They are charge, size and shape. As we see before, electrophoretic mobility is equals to Q by F. Q is nothing but charge and F is nothing but size and shape, right? So if the charge is high, then it moves with higher speed, and the mass is high, then the mobility will be reduced. And shape, for example, globular proteins move faster than the fibrous proteins. These fibrous proteins have higher surface to volume ratio, that's why they experience some kind of resistance from the medium which they are in during separation. And the next, extrinsic factors: buffer, electric field and supporting material. Whenever we are going to choose the buffer, we need to consider the properties of the sample. For example, as we see the proteins charge could change with the pH of the surrounding medium. So we need to make sure that the buffer which we are going to use for the protein separation should have the pH higher or lower than the isoelectric point, not at the isoelectric point, because at that isoelectric point the charge on the protein would be 0 and it won't move at all. And the ionic strength of the buffer should also be considered. The buffer's ionic strength should not exceed the sample's ionic strength. It will slow the migration of the sample's separation. And electric field, this has voltage, current and resistance. This could be explained by a simple Ohm's law. Voltage equals to current into resistance. Here I is current, R is resistance and V is voltage. So V is proportional to the I and inversely proportional to the R. So voltage is proportional to the current. So if we increase the voltage, current would also increase and it would speeds up the migration process of the molecule. But here we need to take care that if the voltage is increased, then there is a chance that the excess energy might dissipate as heat and it will result in the increase of temperature of the surrounding medium. If that happens, then that increased temperature could denature the proteins or nucleic acids under separation. So we should avoid the excess temperatures. And the supporting material. This supporting material gives some time to resolve, which could be helpful to get the better resolution. And it has adsorption. The supporting material should be less adsorptive. Okay. and the pore size, which I am going to talk about in a bit. So, these are the factors influencing electrophoresis. Whenever we are running the electrophoretic system, we need to take care that these factors should be kept constant, and in order to get the maximum migration speed and better resolution. Next, types of electrophoresis. There are various types of electrophoresis. Today we are going to discuss about the basic types: moving boundary electrophoresis and zone electrophoresis. Moving boundary electrophoresis is also called as free electrophoresis because there is no involvement of supporting material here. And zone electrophoresis. In zone electrophoresis, we do use supporting material. Based on the type of supporting material we use, again it could be divided into paper electrophoresis and gel electrophoresis. Here the support is paper, here it is gel. The gel electrophoresis is again divided into horizontal gel electrophoresis and vertical gel electrophoresis. This is based on the direction of the gel run. In horizontal gel electrophoresis, we run the gel in horizontal direction, and in vertical gel electrophoresis, it would be vertical. The best example for horizontal gel electrophoresis is Agarose gel electrophoresis, and the example for vertical is polyacrylamide gel electrophoresis. Let's see each of them in detail. Moving boundary electrophoresis. This technique is used by TSWREIS to separate the serum proteins from horse blood. For this, he constructed a U-shaped tube which is made up of glass, and at the each limbs he added electrodes. To the middle of the tube he added protein plus buffer solution. It has protein. Let's say these proteins carry negative charge. These are dissolved in buffer solution, and on top of which he added the clear buffer. This is clear buffer. So, and here he also attached a optical system called Schilleran optical system. When the current is applied to this system, these proteins move according to the charge on them. This is negative charge carrier, so it moves towards the positively charged electrode, okay, which is anode. When it is moving, this boundary could also move along with it. So, here the boundary is moved from here to here. Through these glass walls, we could see the movement of these boundaries. So, here it is ascending, and in this way it is descending from here to here. That is why this technique is called moving boundary electrophoresis. And this optical system, whenever a protein passes of this system, it gives a peak. It gives a single peak for each protein. In this way, with serum proteins in the horse blood, TSWREIS got 4 peaks for 4 different proteins. Those are albumin, alpha, beta and gamma globulins. This technique is not very widely used now, but it is still used to check the purity of the proteins and also be used to separate the proteins. If the protein is pure, then this optical system would give a single peak, which means the protein is pure. Next, paper electrophoresis. In paper electrophoresis, the supporting material is paper. In order to run the system, first the paper should be dampened with the buffer solution which we are going to use, and the sides, either sides of the paper should be immersed in the gel tank, buffer tank, and this buffer tank is connected to the electrodes. And the sample which we are going to separate should be applied at the middle of the paper, and based on the charge by mass ratio of the sample particles, they move towards either anode or cathode. So positively charged particles move towards this side and negatively charged particles move this side, and based on the mass, bigger molecules migrate slower than the smaller molecules. Once the run is complete, we need to take it out and stain it with the dyes. If it is a protein sample, we have to dye it with the protein dyes, Kumasov brilliant blue or bromophenol blue. Once we dye it with those stains, we could see the colored spots for the separated sample particles. And this technique is easy to perform and also less expensive. And next is Agarose gel electrophoresis. Here we use the reagents Agarose, buffer, fluorescent dye in case of nucleic acids, and sample buffer and DNA ladder. Agarose. The polymer which we are using here is agarose. We have to dissolve the agarose in buffer solution in order to prepare the gel. These gel polymers makes a matrix with pores in it, and the pores could be bigger or smaller based on the percentage of the gel. Here it is having small pores. Let us say this is 1% agarose and it is 3% agarose. Based on the fragment size of the sample, we have to select the pore size. 1% agarose has bigger pores and 3% agarose has lesser pores, smaller pores. And the buffer TAE or TBE, tris acetate EDTA or tris borate EDTA. And the fluorescent ethidium bromide, acridine orange or cyber green, etc. These fluorescent dyes act as intercalating agents and they insert themselves between the stacked bases of DNA. In that way, we could visualize the DNA when it is exposed to the UV light, because DNA itself is not fluorescent. And the sample buffer has bromophenol blue, which act as a tracker, and a glycerol. Glycerol gives density to the sample. And the DNA ladder. This DNA ladder has known size fragments. So, the fragment size is already known in this DNA ladder solution. We can separate various molecules by using agarose gel electrophoresis, but nucleic acids are the best ones to separate by using agarose gel electrophoresis. In order to prepare the gel preparation is also called as gel casting. We need to dissolve the agarose powder in buffer solution and heat it up until near boiling temperature, and once it is boiled, we need to let it cool down and add the fluorescent dye to it and pour the sample into the gel casting tray, which is protected at either ends by the tape, and it is at the one side of the gel casting tray we have wells with the comb. So, once the gel is solidified, we need to dip the gel inside the buffer tank. This buffer tank is connected either sides by the electrodes, cathode and anode. And once the gel is ready, we need to prepare the sample by adding this sample buffer. In this sample buffer, glycerol gives the density to the sample, so that when we add the sample to the wells, the sample goes directly into the bottom of the well instead of diffusing it. In this way, we could reduce the loss of the sample. Here you could see in this picture, once the power supply is on, the sample started migrating. Here, low molecular weight molecules migrate faster than the high molecular weight molecules. Once the gel run is complete, we need to analyze the final image. This would looks like this. It is the gel dark which we use to analyze the samples. And applications of agarose gel electrophoresis. It is one of the most important downstream applications for PCR related techniques like DNA fingerprinting, disease diagnostics, DNA sequencing, and also it is going to be used to check the DNA protein interactions. In DNA fingerprinting, the other applications are paternity testing and adulteration detection. Let's see this image. In this image, these DNA profiles are prepared by the DNA isolated from crime scene and the suspect samples. Here, if we could see carefully, suspect 2 sample identified exactly with the crime scene, matched exactly with the crime scene sample. With this, we might interpret that there is a relationship between a suspect 2 and the crime scene. Here, we isolated hemoglobin protein from sickle cell individuals and normal individuals, and this S and A is the carrier's hemoglobin protein. Sickle cell anemia is a disease caused by the mutation in beta globin chain of hemoglobin protein. So, once we isolate the hemoglobin protein and run it on the gel surface, we could see the differential migration for the abnormal protein and normal protein. In this way, we could also identify the carrier proteins. Here, this first well is having the carrier protein, and this one is sickle cell protein, and this one is a normal hemoglobin protein. And this could also be used to analyze the DNA protein interactions. Once the protein is binds with the DNA, its molecular mass would increase and it would migrate slower than the normal DNA molecule. Here is a self-assessment for you. These are all potential questions for your PG preparation. Whenever you study something, try to apply that. That will help you to understand a lot. Thank you for giving this opportunity. Thank you.